Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. I am teaching Chemical Engineering Thermodynamics 1 and this is my lecture 7. Okay, so now we will start our lecture. So in the previous lecture we have discussed about the enthalpy and the effects at constant volume and constant pressure, and we have also uh, did some examples related to this at constant volume and constant pressure related to the enthalpy and heat capacity. Also we have defined the what is the heat capacity and how you can relate in your surroundings, and related examples of the heat capacity we have did. And in between we will also discuss about the measures of flow. So these things we have discussed in the previous lecture. So and we have also defined the specific heat at constant volume, which is the change in internal energy and change in temperature. And we have also discussed about the at constant pressure specific heat, which is del H upon del T at constant pressure. So these things we have discussed related to the heat capacity we have discussed in the previous lecture, and we have also solved the examples related to this, and we have also discussed the measures of flow. So the mass flow rate, molar flow rate, and volumetric flow rate, and the velocity we have defined in the lecture 6. And this is a mass flow rate and the molar flow rate. We have discussed this and related these flow rates. We have also calculated some examples. We have solved some example. Okay. So in today lecture we will discuss about the mass balance for open system and the general energy balance for steady state flow process, and related to these examples of this. So this thing we will discuss today. Okay. So now I will tell you about the what is the mass balance for the open system, how we can define the mass balance for an open system. So the region of a space is identified for analysis of open system is called control volume. It is separated from its surroundings by a control surface. The fluid within the control volume is thermodynamic system for which mass and energy balance are written. Because mass is conserved and the rate of change of mass within the control volume del m cv divided by dt equals the net rate of flow of mass into the control volume. So the convention is that the flow is positive when the directed into the control volume and negative when directed out. So this is a system. So this is the white color area is control volume, and this black line is called the control surface, and surrounding it is a surrounding, the surrounding is which is separated from our this control surface is separated from the surroundings, our control volume. Okay, and these are some masses, which is m1 and m2 and m3, and this arrow shows the direction at which direction it is flowing. It is inside or it is outside. so you can easily see. Okay, now if you will describe this figure, so it is a schematic representation of control volume. It is separated from its surroundings by extensible control surface. Two stream with flow rates M1 and M2 are shown directly into the control volume, and one stream with flow rates M3 is directed out. Okay, so the mass balance is expressed mathematically by this equation. You are seeing this. So del M and del T, which is the change in the mass at control volume, and this is a changes in mass flow rate, and Fs represent the flowing stream, which is equal to 0. So this is a mathematical expression of mass balance. For the control volume, the second term, so this term, which you can represent, if you will see the control volume, so you have seen that one. So there is a M1, M2 is in and M3 is out. So you can also write M3 is a positive direction, in out is positive direction, and M1, M2 is in negative direction. So you can easily write like this. The difference operator del, this del here signifies the difference between exit and entrance flow, and the subscript Fs indicates that the terms applies to all following streams, this Fs. So note that this is a different usage of the operator compared with previous section. In the previous section we have also used these type of terms, so that is separated, but this is the different terms we are using here. So where the difference was between an initial state and the final state, both usage of the difference operator are common, and care must be taken to ensure that the correct sense is understood. When the mass flow rate M is given in the previous equation, the one, and equation 2a, which is, you can write M dot UA rho. So you know about, in the previous section mass flow rate we have discussed, and volumetric flow rate. So mass flow rate is the volume into the density, and volume, because change in the volume, so volume is area into the length. So the change in the length, the elevation or height, so that we will call velocity. So UA rho, so this mass flow rate will be the UA rho. So if you will put in the equation 1, so what you will get, del M CV upon del T plus del rho UA Fs. Fs is flow stream, and this, instead of M dot we have put it this, and which is equal to 0. In this form, the mass flow balance equation is often called continuity equation. So this is the form of continuity equation. So next, the steady state. For the steady state flow process are those for which condition within the control volume do not change with time. So these are an important class of flow process often encountered in practice. So in a steady state process, the control volume contains a constant mass of fluid. So, and the first of or accumulation terms of equation 2a is 0 and reducing to the equation 2. So when you are talking about the steady state, you are seeing this term will be, there is a no flow, the control volume, the mass is constant, so there is a no change in the mass with respect to the time. So only the del rho UA will be remaining, and you can simplify like this, del rho UA Fs equal to 0. So the term steady state does not necessarily implies that the flow rate are constants. merely that the inflow of mass is exactly matched by the outflow of mass. So this is the thing. So where there is a single entrance and a single exit stream, the mass flow rates, if you will, mass flow rate is m dot, is the same for the both stream. Then so m dot constant, so rho 2 u2 a2 equal to rho 1 u1 a1. If you will if you will say that 1 represent for in and 2 represent for out, so you can easily write rho 2 u2 a2 equal to rho 1 u1 a1. For the specific volume is the reciprocal of the density. Okay, so the m dot, which is equal to u1 a1 v1, which is equal to u2 a2 v2 equal to ua v. So this is the form of continuity equation find frequent use. It is a very common use of this continuity equation. Generally in fluid mechanics we very frequently use this equation for calculating the mass flow rate for the outlets or intermediate points. We can also calculate the mass flow rate, or what will be the, for the designing of the pipe we can also this equation, this continuity equation we can also use. So now we will discuss about the general energy balance. Because energy like mass is conserved, the rate of change of energy within the control volume equals the rate of energy transfer into the control volume. A stream flowing into and out of flow out of the control volume have associated with them energy in its internal potential and kinetic forms, and all may contribute to the energy changes of the system, and each unit mass of a stream carries with it total energy. So this is a total energy U plus 1 upon 2 U square plus ZG. Okay, so these are the internal energy is U, and this is kinetic energy 1 by 2 U square plus this is a potential energy ZG. Okay, so where U is the average velocity of the stream, and Z is the its elevation above a datum level, and G is the local acceleration of gravity. So each stream transport energy at the rate. So you can write like this. So rate will be like this, m dot, you have to multiply with the mass flow rate, and the net energy transport into the system by the flowing stream is therefore, so you can write for the flowing stream minus del u plus 1 by 2 u square plus zg m dot fs. So this will be the flowing stream, where the effect of the minus sign with del is to make the terms read in out. Okay, so the rate of energy accumulation within the control volume includes this quantity in addition to the heat transfer rate Q and workout rate. So you can write like this. So this energy equation will be del mu, for it is for the control volume, upon T. So this is a rate of change of potential energy for the control volume, and minus del u plus 1 by 2 u square plus zg m dot fs plus heat plus work rate, heat transfer rate and the work rate. Okay, so this is a potential energy, this is a kinetic energy, no, this is a internal energy, it is a kinetic energy, and it is a potential energy, and this is a heat transfer rate, and this is a work rate. So all these terms are we have to include for the general energy equation. The work may include of several forms. This work is associated with moving the flowing stream through entrance and exit. The fluid at any entrance or exit has a set of average properties: pressure, volume, internal energy and enthalpy, and others also. So this is our system. So this is a control volume and this is a surrounding, and this black line shows the control surface, and this is the inlet and this is the outlet. So so this is a piston, you are applying a pressure, and inside this the initial volume is V, and velocity and enthalpy and internal energy is given here, and there is a Q is in heat is transferring, and this is whatever the work done is inside this. So and this is the outlet. When the it is all here also we are applying the pressure P2, and this is the V2, U2 and S2, whatever the changes in and internal energy, enthalpy and the velocity, you can see your volume for this system. Okay, now this is the control volume with one entrance and one exit. So this is, so imagine that a unit mass of fluid with these properties exists at an entrance or exist as shown in figure. This unit mass of fluid is acted upon by additional fluid, here replaced by a piston that exerts the constant pressure. The work done by this piston in moving the unit mass through the entrance is PV, and the work rate is PV m dot. Okay, because this del denotes the difference between the exit and entrance quantities, so the net work done on the system when all entrance and exit section are taken into account, so you can write minus del PV m dot for the flow stream, Fs will be the flow stream. So another form of the work is shaft works, indicate in the figure by rate W. Okay, so work may be associated with expansion or contraction of the entire control volume. So these forms of work are all includes in rate terms represented by W. The preceding equation may now can be written. So del m u cv upon del t, in this term will remain, and this term minus del u plus 1 by 2 u square plus zg m dot fs, it will be also remain. This q dot the same, but only this minus del pv m dot fs plus w dot. So these two terms we have to include inside for the work done. So this is the total work done which is done by our system. So the definition of enthalpy, H equal to U plus PV, so we know this. So if you will put this one instead of internal energy, if you will write U here, so what will happen? H plus 1 by 2 U square plus ZG m dot equal to Q dot plus W. Okay, and this is actually here it is a plus sign, it is a plus sign here, it is not equal to, it is a plus sign, this is a mistake. So if del m u cv upon del t, and you will rearrange the equation, so here you can put, so plus del H plus 1 by 2 u square plus Zg m dot Fs, which is equal to Q plus W. Okay, so you will get this. Actually, you are seeing the in the previous equation we have added the PV terms and U terms, so that includes the, if you will combine this you will get H. Okay, so this is the thing you will see. So the velocity u is in the kinetic energy terms is the bulk mean velocity as defined by the equation u equal to m upon rho a. So instead of m you can write also u, instead of you can also write like this. The fluid flowing in pipes exhibits a velocity profile that rises from 0 at the wall, the no slip condition to the maximum at the center of the pipe. So the kinetic energy of the fluid in a pipe depends on the velocity profile. For the case of laminar flow, the profile is parabolic and the integration across the pipe shows that the kinetic energy term should properly by U2. In fully developed turbulent flow, the more common cases are in practice we have seen. So the velocity across the major portion of the pipe is not far from uniform, and the expression U2 divided by 2 as used in the energy equation is more nearly correct. Although in the previous equation, the 2.27 equation, the energy balance for the reasonable general, this is that will be the general equation, but it has some limitations also. In a particular case, it reflects the tacit assumptions that the center of mass of the control volume is stationary. If you will say that the assumption is center of mass of the control volume is stationary, thus no terms for the kinetic and potential energy change of the fluids in the control volumes are included. For virtually all application of interest to chemical engineers to the 2.27 equation is very important. For many applications, kinetic and potential energy changes in the flowing streams are also negligible. In some cases, we also negligible only. So if you will simplify that equation in the previous equation, general equation, so that terms will be kinetic energy and potential energy terms will be cancel out. So these two terms, so u square and zg terms will be cancel out, only h will remain and q plus w will remain. Okay, so only this term will be remain. Okay, so this is our when we are neglecting the kinetic and potential energy for the system. So now we will do some examples related to this general energy balance. For an insulated or electrically heated tank for hot water contains 190 kilogram of liquid water at 60 degree centigrade. Imagine you are taking a shower using the water from this tank when a power outage occurs. So if water is withdrawn from the tank at a steady state of m dot, which is equal to 0.2 kilogram per second inverse, so how long will it take for the temperature of the water in the tank to drop from 60 to 35 degrees centigrade? So if you are cooling the water, how much time requires? So this is a example. So assumptions are the cold water enters tank at 10 degrees centigrade and that heat losses from the tank are negligible. Here an excellent assumptions for liquid water is that the Cv Cp equal to C. So at constant volume and constant pressure, the heat capacity will be the remain constant, the same, so which is independent upon temperature and pressure. So now we will solve this system. So this is an example of application of equation 2.28. Okay, in the previous equation, when the negligible potential energy and the kinetic energy. So Q equal to W equal to 0 at the transit process. We assume perfect mixing of the content of the tank. This implies that the properties of the water leaving the tank are those of the water in the tank. With the mass flow rate into the tank equals to the mass flow rate out, MCV is constant. So moreover, the difference between the inlet and outlet kinetics and potential energies can be negligible. So we have already, so this 2.2 equation will be used there. So equation 1 is therefore written, so this one. So here only the enthalpy terms and the heat and work is there, and rate of change of potential energy is there. No kinetic and potential energy is there in this equation. But heat is there is no heat loss, there is no heat transferring, and the work done is also 0 because it is a transient process. So you can write this equation like this: del m del u upon del t plus m dot h minus h1. Okay, so where the unsubscripted quantities refers to the content of the tank, where we have not subscribed anything, so that will be the inside the tank, and the water leaving the tank, you can see that. And the H1 is specific enthalpy of the water which is entering the tank, which is inside this tank, which is H1, with CV equal to Cp equal to C. So del U upon del T equal to C del T upon del T. So H minus H1 equal to C T minus T1. You can also write like this. So the energy balance then becomes on rearrangement del T equal to minus M dot M del T upon T minus T1. So if you will integrate this equation from T0, where T equal to T0 to arbitrary time T is yield, so T equal to M minus M upon M dot ln T minus T1 T0 minus T1. Substitute so numerical value of into the equation for the condition of the problems. So the conditions of the equation are given, which is minus 190 and 0.2 ln 35 minus 10 60 minus 10. These conditions are already given in and so you will get the total time 658.5 seconds. So thus the water temperature in the tank will drop from 60 degree to 35 degree centigrade after about 11 minutes. If you will divide it by 658.5 divided by 60, so it is 11 minutes around to cool the water. So this is the dropping of the water we can easily calculate. Okay, so now if we will and the next topic we will read energy balance for steady state flow process. The flow process for which the accumulation terms of equation 2.27 del mu Cv del T is 0 are said to occur as steady state. Steady state we have already discussed when there is no change in the changes with the time in internal energy, so that terms will be 0. So this is a 2.27 equation. You can see here del m u upon del T plus del H plus 1 by 2 u square plus Zg m dot Fs equal to q dot plus w dot. So this is a full equation. Only these terms will be 0 because it is in steady state. As discussed with the respect of the mass balance, this means that mass of the system within the control volume is constant. It also means that no changes occurs with time. So this term is 0 because there is no change with the time. And the properties of fluid within the control volume nor its entrance or exist. So that there is no expansion of control volume is possible under these circumstances. So the only work of the process is shaft work, and the general energy balance equation becomes, so now equation becomes like this, that changes internal energy will be 0 with the time, that is 0. So although steady state does not necessarily imply steady flow, is not so the usual application of this equation is steady state steady flow process, because such process represent the industrial norms. For further specialization results when the control volume has one entrance and one exit. The same mass flow rate m dot then applies to both streams, and equation 2.29 reduces to. So this is the equation now reduces del H plus 1 by 2 u square plus Zj m equal to q dot plus w dash s. So this is will be the equation you can write for the system, for the steady state system. So where this Fs subscript the flowing is has been omitted in these simple cases, and the del denoted the changes from the entrance to the exit. And if you will divide by this mass flow rate m dot, so del H plus 1 by 2 u square plus Zg bracket close equal to q dot upon m dot plus w s dot upon m dot, which is equal to q plus ws. Okay, so you can also write, if you will rearrange this equation, so del H plus del u square by 2 plus g del z equal to q plus ws. So this is a final equation for a steady state process when there is no flowing streams there. So the equation is the mathematical expression of the first law for a steady state. So steady flow process between one entrance and one exit. So all terms represent energy per unit mass of fluids. So the energy unit is usually the joule. So if you will the whole equation unit will be the joule. So in many applications the kinetic and potential terms are omitted because they are negligible compared with the other terms. So in the previous examples there is no kinetic and potential energy terms are there, so we have used that one, but there is a rate of change of with the time. So we have calculated how much time required to cool the system. So but here in this system the energy, if some cases we will there is no terms is there, so that equation directly becomes del H equal to q plus ws. So and this expression of the first law for a steady state flow process in analogous to equation 2.3. It is very similar to the the an internal energy equation, so which is del U equal to Q plus W for the known flow process. We have already discussed this equation in the previous cases. Okay. However, in the equation 2.3, the enthalpy rather than the internal energy is the thermodynamic property of the of importance. So del refers to a change from inlet to the outlet rather than from before to the after an event. Okay. So today lecture we have so in today lecture we have discussed about some examples and the mass balance for open system and mass energy balance for open system, the closed system, and the general energy balance equation we have did, and we have also the energy balance for the steady state. We have also discussed this term, and the mass balance for the steady state we have also is discussed that term also. The continuity equation, we have described, and this general energy equation we have described here. This is the general energy equation, and in some cases when there is no kinetic and potential energy are there, so in that case we have did only this term will be negligible, so you can directly, this will be the equation you will see, and for the steady state, so this term will be 0, you can see, and this is the continuity equation, m dot equal to u1 a1 upon v1 equal to u2 a2 upon v2 equal to ua upon v, where this is a specific volume, and instead of v1 you can also write rho, which is a density. You can also write like this, that can also you can write. So because specific volume is reciprocal to the density, we have also seen in the previous derivation, we have seen in the slides, we have seen, and in the previous lecture we have also discussed this specific heat capacity. So this is very important topic, and these are very important equations. Generally these equations also important for the gate purpose also. If you can drive these equation, this general energy equation you can drive, so that can be very useful for your solving many heat this thermodynamics problems or the heat transfer problem you can easily solve. And if you know how to balance mass balance or energy balance, you can do so in your near future. You can know you cannot get any problem, you cannot stuck, and you can easily solve problems, and this is very important for the industrial uses also. If you know about this energy equation, which is directly affects the cost of the process also, so this equation is very important, because if you will use less energy, and you in the less energy you can flow your process, or you will run your process for the less energy, so that will be very useful. They reduces the cost and improve the efficiency of your product. So this energy equation is very important for designing purpose, for many systems, for the heat transfer, for the heat exchanger, condenser, distillation, or adsorbers, where you are required the energy. So this equation is very important, and the mass energy, the continuity equation is for the flow rates for in a pipe, and the designing for the many equipment of the flow instrument also. You can also use this continuity equation you use. So these are very important equation, which is very useful for your near future. So in the next lecture we will discuss about what different so we have discussed in the today we have discussed this steady state flow process, and in the next lecture we will discuss how we can utilize at steady state flow process, and we will do some examples related to this, and we will also try to solve some unsolved problem of the energy balance and the mass balance. Okay, so this thing we will do in the next lecture. So thank you very much. If you have any doubt related to the this thermodynamics or today topic, this energy balance and the mass balance, and general energy, how can try the general energy equation, any doubt you can tell me. I will rectify your doubt. And this is my email id. So this is chemicalsaniraj@gmail.com, and this is my website. You can also some reading things you can also read here. So thank you very much for listening.